This video is all about gears, and we're going to look at torque and speed on a simple gear system. Now, consider this. Imagine we have, let's say, a motor or a handle causing this gear to turn. Because of the way they interlock, this gear will in turn cause that one to turn. To try and understand your strength of your ability to make it turn, and in physics we call that torque, have a close look at this gear. At the very center, that's the fulcrum, because it's going to rotate about the center. And where these teeth interconnect, that's where the force is applied. See, if this gear here is rotating this way, then this tooth is going to apply a force right here. The force that it applies is this distance here from the fulcrum. So it's going to impart torque on that gear, causing it to turn. What we're going to look at today is we're going to make an assumption. We'll assume that we know how much torque is rotating one of the gears, and we're going to determine how much torque that will put on the other gear. Torque depends on the lever arm. It depends on how far the force is from the fulcrum. How far you are from the center is proportional to the number of teeth that there are on the gear. Assuming that these gears match, meaning that the teeth and the space between the teeth are the same size so that these gears can mesh together, whichever one has more teeth is going to have a greater radius and therefore a greater lever arm length. Whichever one has fewer teeth is going to have a lesser radius and therefore a shorter lever arm. So the way we analyze this, we call the gear ratio. We define that as the number of teeth being driven. And we divide that by the number of teeth driving. So in this example here, let's say we were to attach a handle onto here, and we were to grab onto and turn that handle. This one is doing the driving. Imagine a handle or a motor attached to this gear. It's driving. This one, maybe if that's a handle, maybe it's attached to a spool to wind up a cable or a rope, or perhaps it's attached to a wheel. This one is being driven. So the gear ratio for this system is equal to the number of teeth being driven. There are 12 on here, divided by the number of teeth driving. There are 8 on here. If I was to switch and put the handle here, that would flip this fraction over, because then we would have 12 teeth driving 8. But in this example, I've got 8 teeth driving 12. What do we do with the gear ratio? The output torque, so that's tau, it stands for torque. The output torque is equal to the input torque multiplied by the gear ratio. So on this handle, let's say I've got 10 Newton meters of torque on that handle. So let's say that our input torque is 10 Newton meters, and our gear ratio is 12 over 8. Now 12 over 8, they're both multiples of 4, so that's actually 3 over 2. our output torque is going to be equal to 10 times 3 over 2. 10 times 3 is 30, divide that by 2 is 15 Newton meters. So what that means is a gear system like this can take 10 Newton meters of torque and turn it into 15, no pun intended, turn it into 15 Newton meters of torque. So the torque goes up. However, you never get anything for free in physics. It comes at a loss. The loss is in speed. A gear system that will give you more torque at the output, whenever it gives you more torque, it will also give you less speed. Now, the reason for that is quite clear if you think about it. The smaller gear will rotate more times than the bigger gear when the teeth are interlocked. This will turn more than one revolution to get this to turn one revolution. The ratio here is 3 over 2. What that means is this has to rotate 3 times to get this to rotate 2 times. So with those teeth interlocked, this gear will always be turning faster than that one. If the motor is attached to the smaller gear, the larger gear will spin slower. You will get less speed, but you will get more torque. The way we calculate that, the speed out is equal to the speed in divided by the gear ratio. So let's say in this example, we're rotating this, and we measure the speed of rotation in revolutions per minute. Let's say we're rotating this at a rate of 1 turn per second. So that would mean our speed in at 1 revolution per second would be 60 revolutions per minute. Our speed out will be equal to our speed in divided by our gear ratio. So we're now dividing, be careful here, our gear ratio was 12 over 8. We're now dividing by 12 over 8. You know how to divide by a fraction? You flip it and you multiply. So if I am dividing by 12 over 8, I am multiplying by 8 over 12. And so my output speed here is going to be 60 times 8 divided by 12. It's 40. So notice our speed went down. We went from 60 RPMs down to 40 RPMs, but our torque went up. We went from 10 Newton meters of torque up to 15. If you've ever ridden a bicycle in a low gear, now what we call a low gear in sort of layman's terms is actually a higher gear ratio. So when you set say you put your car or your dirt bike in first, or you set your mountain bike to a low gear, you don't go fast, but your ability to climb hills is really high, your ability to pull things is really great, and your ability to start from a standstill is as high as it'll be. You get more torque, but you get less speed. Now, for those of you in my class, you're going to work your way through this chart to just better understand this. If you're on YouTube and not in my class, you might want to pause it, copy this chart out, and then I'm going to show you how to work your way through it. So I've got some questions here, 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 and here. So we're going to work our way with, we'll start out with just teeth and gear ratios, and then we're going to work our way up to deal with the radius of a wheel, circumference of a wheel, distance traveled, convert from rotations to linear motion. Okay, so in the first questions, we've got input torque, driving gear, driven gear, gear ratio, and output torque. So let's just pick a few random ones and you can do the rest yourselves. If my input torque is 500, I have 20 teeth driving and 30 teeth being driven. My gear ratio is driven over driving, so my gear ratio is 30 over 20. Now, if you're good at math, you might look at that and right away say, oh, 30 over 20 is 3 over 2. If you reduce the fraction, it's easier, but if you don't, you're still going to get this right. How do I get my output torque? We multiply the gear ratio by the input torque to get the output torque. So I'm going to take 3 over 2 and multiply that by my input torque of 500. Gives me an output torque of 750. Okay, now this next question is a little tricky. I've got an input torque of 300 and output torque of 500. So maybe you're designing a machine and your motor's providing you with 300 newton meters of torque, but over on, say, some spool, you require 500 newton meters of torque. We have 50 teeth being driven. So let's figure out what we can first here. We know that the gear ratio is the number of teeth being driven over the number of teeth driving, but we're missing too much information to use that. However, we also know that the output torque is equal to the input torque multiplied by the gear ratio. If you divide the input torque, the gear ratio is the output torque divided by the input torque. So my gear ratio is my output torque divided by my input torque. So in this question, my gear ratio is 500 over 300, which is 5 over 3. I have 50 teeth on my driven gear. And remember, we also know the gear ratio is the teeth driven over the teeth driving. So I've got 50 teeth being driven. I've got a gear ratio of 5 over 3. And I want to know how many teeth are driving. Can you see it? That's got to be 30. 50 divided by 30 is equal to 5 divided by 3. If you don't see it, that's okay. If you multiplied both sides by driving, you would get 5 over 3 times the number of teeth driving is equal to 50. And then if you were to divide both sides by 5 over 3, you'd multiply both sides by 3 over 5. So driving is 50 times 3 over 5. That's giving you 30. So I've got 30 teeth driving, 50 teeth being driven, and that's giving me the required gear ratio of 5 over 3, which will give us the required output torque of 500 when our input torque is 300. The rest of these work like that. As you're answering these questions, notice I didn't give you the driving or the driven gear. You get to make it up. You can put any number you want for one of these and then calculate to determine the value that goes with it for the other. So for example, if you had a gear ratio of 10, you could say you have 10 teeth driving and 100 teeth being driven, because 100 divided by 10 gives you 10. You just have to make the fraction work for those. These questions are the same, except I gave you speed, not torque. And remember, things go the other way. So for these questions, the output speed is equal to the input speed divided by the gear ratio. Let's do this one here with all these blanks. So I've got an input speed of 5 and an output speed of 25. So my speed in is 5 and my speed out is 25. So that means that I'm turning a handle and the wheel that it's attached to is going 5 times as fast. Now remember, the speed out is equal to the speed in divided by the gear ratio. So if I rearrange this to get gear ratio by itself, the gear ratio is the speed in divided by the speed out. So it is, the speed in is 5, the speed out is 25. My gear ratio is 5 divided by 25, which is 1/5. Remember, a big gear ratio gives you more torque and less speed. So the opposite of that must also be true. A small gear ratio gives you less torque but more speed. And that's what we have here, a small gear ratio. So we're going to have much less output torque, but we get much more output speed. So my gear ratio is 1/5. That means that, remember, the gear ratio is the number of teeth driven over the number of teeth driving. And for a gear ratio of 1/5, that implies perhaps I could have one tooth being driven by 5 teeth driving. But that doesn't really work, not in practice. So we're going to need more teeth than that. So let's make that realistic by multiplying top and bottom by 10. So now I have 10 teeth being driven, 50 teeth driving. That's going to give me a gear ratio of 1/5. And a gear ratio of 1/5 is going to give us an output speed of 25 when we have an input speed of 5. So on this question here, I have a gear ratio of 1/5. So I have 10 teeth being driven by 50 teeth doing the driving. 10/50 is 1/5. And 5 divided by 1/5 gives us 25. Okay, the questions over here are now relating torque to force. And the way this works, imagine I have a tire. Okay, so this is a bicycle tire. And I think they're typically about 26 inches, so that's about 13 inches. So let's say that is, it's approximately 35 centimeters in radius. So let's say I have a bicycle tire. And the radius, that's the distance from the center to the end, is 35 centimeters. How much force is this tire going to put on the road for a given amount of torque that's being applied by the chain to the sprocket? See, what happens here is there's tension in the chain, so you have force on the chain. That force will apply torque to the sprocket, which in turn applies torque to the wheel, which will put force on the road. If I have a radius of 35 centimeters, and let's say I want to put 100 newtons of force on the road, how much torque do I need on this wheel? You know that torque is equal to force times distance. If I have 100 newtons of force at a distance of 0.35 meters, remember 35 centimeters is 0.35 meters, that's going to give me 35 Newton meters of torque. So if I have 35 Newton meters of torque here, at that distance, I'm going to put 100 newtons of force on the road. I'll save the other problems for another video where we're going to deal with the circumference to determine the distance traveled and the speed so that we can find linear speed based on the speed of rotation.